Welcome to today's Explainer. I am absolutely thrilled to have you here. You know, if you've ever wondered how the massive tech giants out there, companies like Uber, Meta, and Netflix, actually scale their artificial intelligence so reliably, well, you are in exactly the right place. Today, we're going to demystify the complex architecture of AI infrastructure. We're going to break down feature stores and model serving platforms using the exact structural blueprints that industry leaders rely on. Okay, let's dive into this. When we think of AI, we almost always picture those glamorous algorithms, deep neural networks, and massive computing power. But there's actually a silent killer lurking in the shadows of data infrastructure, and it completely shatters the illusion that AI is just about writing clever code. That silent killer? It's called training serving skew. Imagine perfecting a delicate recipe in your quiet home kitchen. You're using precisely measured ingredients, you have all the time in the world. Now imagine trying to recreate that exact same dish on a chaotic restaurant line during a Friday night dinner rush, where you're just kind of guessing the measurements on the fly. The result is going to be completely different, right? Well, in machine learning, if the data features used to train a model are computed differently than the data features fed into the model when it's live, your model's accuracy will just silently decay and plummet. So here is our roadmap for today. First, we'll diagnose the silent AI killer. Second, we'll introduce the unified platform solution. Third, we'll assemble the architecture piece by piece. Fourth, we'll look at storage and serving. And finally, the safety guardrails that keep the whole thing from crashing down. Starting off with Section 1. The silent AI killer, training serving skew. The fundamental villain of our story here is the naive, do-it-yourself approach. Think about it. If a data scientist computes features in an offline training notebook, and then a completely different software engineer tries to rewrite that exact same logic for the live serving system, well, you're practically begging for skew. It is literally a recipe for disaster, where the logic will inevitably drift. The crucial point here is really understanding this contrast. The gritty reality of that DIY approach is massive duplicated effort and super high error rates, mostly because everyone is recomputing data differently. But the true value of a dedicated AI platform, it's incredibly simple but powerful. It's a single, unified feature definition that's shared across both the training path and the live serving path. You define it once, and the system handles the rest. Moving right along to Section 2, the unified platform solution, eliminating skew. The goal of a world-class system is honestly quite straightforward. Provide a shared platform for defining, computing, storing, and serving ML features completely consistently. This eliminates that training serving skew while massively accelerating your engineering teams. Systems like Uber's Michelangelo or Meta's FB Learner, they were built with this exact philosophy in mind. They're aiming for high feature reuse and incredibly fast model onboarding. A huge part of making this unified platform work is maintaining what we call point-in-time correctness. And guys, this is a massive deal. Without it, your system might accidentally time travel during training by pulling in future data that the model wouldn't have actually had access to when a prediction was made in the real world. We call this label leakage. It artificially inflates your training accuracy, only for the model to completely fail once it goes live. Point-in-time correctness absolutely locks this down. Let's move to Section 3 and see how this builds. Architecture assembly, building the platform. It all starts right here at the ingestion layer with our data sources. A unified platform really needs to seamlessly ingest both high-throughput, real-time event streams, like say clicks on a website happening right this second, as well as massive historical batch data that's just sitting in warehouse tables. Once that raw data is ingested, it hits the shared feature transform layer. You can think of this as the beating heart of ensuring consistency. Instead of having separate code bases, both your stream and batch data run through this exact same centralized transformation logic to become usable machine learning features. After those features are transformed, they get routed using a brilliant dual storage strategy. First, they go to the offline store. This is a massive warehouse holding petabytes of historical data specifically for training. Second, they head to the online store, which is a highly optimized in-memory store holding only recent data for lightning-fast live serving. Now, when it's time for data scientists to actually build a new model, they tap into that offline store. The platform performs those crucial point-in-time joins we discussed earlier, safely stitching together historical features and labels to create bulletproof training datasets without any accidental time travel. Finally, we reach the edge of our architecture, model serving. Out in production, a live request comes in. The model serving layer rapidly fetches the latest data from the online store. We're usually talking under 10 to 50 milliseconds here, and the model generates a prediction right on the spot. Next up is Section 4, Storage and Serving, Managing Features. Now, what's really interesting to look at here is the concept of on-demand features. See, not everything can be pre-calculated. Think of a ride-sharing app. You obviously can't calculate the exact distance between a driver and a rider until the very second the rider opens the app. Because these are calculated at request time, they absolutely must run the exact same shared code in both the training and the serving environments. No exceptions. Architects face this constant balancing tension between cost, data freshness, and engineering effort. Streaming absolutely everything just to get second-level freshness, that adds massive operational cost and complexity. But the reality is, not every single feature actually needs to be updated by the millisecond. A truly great platform lets teams choose the appropriate freshness per feature, perfectly balancing those tricky trade-offs. Okay, so once the features are ready and the model is trained, you definitely don't just flip a switch and pray. Tech giants use super strict guardrails for safe model rollouts. They'll start with a shadow deployment, where the new model processes live data, but doesn't actually impact the user's experience. Then a canary release to a tiny fraction of users. Then comes rigorous A/B testing. And crucially, even at full rollout, the platform must have an instant rollback capability. If metrics suddenly drop, boom, the system reverts to the previous version immediately. And that brings us to our final section, Section 5, Safety Guardrails, Monitoring the Platform. The key to all of this is constantly watching for failure modes. For example, if training serving skew occurs, the impact is silent model decay. To fight this, a world-class platform uses a parity monitor. It logs the online feature values generated live and later compares them against recomputed offline values to detect any kind of divergence. Listen, detecting skew isn't a luxury. If a platform can't continuously measure and detect skew, it really cannot claim to prevent it. So how do we actually evaluate success? It boils down to a few hard metrics. Skew rate must be kept at 0. Feature relatency has to stay reliably under 50 milliseconds. But it's also about tangible business value. How fast can an engineer deploy a new model? And what's the feature reuse rate? If 5 different teams are reusing the same user demographic feature instead of building it from scratch 5 separate times, that is massive platform ROI. It completely maximizes productivity. We have covered a lot of ground today, from diagnosing the silent killer of training serving skew all the way to assembling a unified architecture that powers the biggest tech platforms in the world. But I want to leave you with this provocative thought. Algorithms are going to evolve, and the models of tomorrow will certainly change. But when that happens, will your underlying data infrastructure be agile and rock solid enough to support them seamlessly? Or will your teams be stuck rebuilding the wheel from scratch every single time? The true future of AI might just rely entirely on the unsung hero of robust data infrastructure. Thanks so much for joining me on this explainer. Keep learning, and I will see you next time.